InSAR, interferometric synthetic aperture radar, became much more popular in the mid-90s when the European Space Agency, the Canadian Space Agency, and NASA launched a bunch of satellites to monitor the Earth. And the main thing they were looking for at first was to use synthetic aperture radar, or SAR data, to measure differences on the Earth's surface. So the first application was creating digital elevation models, or DEMs, and NASA did this with their SRTM satellite mission. Another application of using radar imagery is to monitor the deformation, the ground deformation across the Earth. So InSAR is a technique that uses multiple radar images to measure the difference in amplitude or phase of the radar images. For InSAR, they specifically use the phase, and the phase difference actually allows you to measure the displacement or the difference in distance between the satellite and the target over time. The goal with InSAR is to use multiple images and to measure the phase displacement, and with that you can get ground deformation. The two most common techniques that people use for InSAR processing is either a two-pass interferometry or interferometric stacking. Two-pass interferometry uses two radar images, and you measure the phase difference between those two images, and what you get is a product called an interferogram, which shows the phase shift over the two acquisitions, and you can convert that into a ground deformation map. The second technique is interferometric stacking, where instead of using two images like the previous technique, you use at least 20 images over a longer period of time, and with this technique you can actually measure small ground deformations down to a millimeter scale.
The use of InSAR as a tool for geotechnical asset management in the transportation environment has not been fully explored. There have been recent studies that are looking at its opportunity, and we believe it could be a very valuable tool.
So in the case of geotechnical asset management, we hope to use InSAR in order to measure ground deformation on which the assets are actually sitting on. So there are one of two approaches that we're trying. The first one is to actually measure the deformation across the asset itself, and this would work well on larger assets like bridges or slopes, assets that spatially are vast in the sense that we can pick up multiple pixels and see multiple radar returns off of them. The other approach would be for smaller assets, such as roads and pavements, pipelines, things that aren't so spatially broad, is to measure the ground deformation on which these assets are sitting on. We hope to gain some sort of insight as to the condition of the asset if we can monitor ground deformation over a long period of time.
InSAR gives us the ability to measure precise deformation. If we can measure deformation of a geotechnical asset over time, it would give us an indication of how that asset is performing. From these deformation measurements, we can compute cumulative displacements over time. We can also compute the velocity or the rate of displacement, which are all indication of the health of an asset. In addition, we can also compare these deformations with assets in the nearby area to see how an asset is performing in comparison to other geotechnical assets within that region. In terms of a strategy to use InSAR for geotechnical asset management, we could use InSAR to screen for sites, to identify sites that are vulnerable. The resources that the transportation agencies have for monitoring assets can be utilized better. The site crew can be sent to specific sites that show movements rather than sending to every single asset that they have.
For the purposes of InSAR, no field equipment is required if using the satellite-based technique, which we're using in this case. The only thing that is required post-acquisition is a specialized software, which is used to process the radar images so you can generate interferograms or displacement maps.
There are commercial companies that do InSAR processing that can be utilized by the transportation agencies to do their annual maintenance.
As with any remote sensing technique, InSAR has a few limitations users must work around. Two prominent limitations for InSAR stacking techniques are issues with decorrelation and blind processing. Decorrelation between radar images may occur at locations where the ground surface geometry or physical surface properties alters too drastically between images. Examples include slopes with rockfalls, where the movement is too rapid, or regions of dense vegetation, where many surface properties change from many factors. Blind processing is just the fact that the user does not know the location of data points prior to processing, which means there is no guarantee that data will be available for all the geotechnical assets a user is interested in.
We evaluated the applicability of InSAR in Nevada, and we found that in a transportation corridor, we were able to identify several critical sites that the transportation agency needs to focus with more ground-based field data collection.
The benefit of using InSAR is you don't have to go into the field multiple times. And in the case for our project, we want to show transportation agencies that without going into the field multiple times, you can save money, you can monitor large areas, and you can measure small deformation rates down to 1 millimeter per year.